Hi, my name is Robin True, and today we're carrying on with section 3 to 5 in our course on fire dynamics. As you recall, in your online learning, we covered section 1 and 2. The learning outcomes there included explaining how a fire starts and is self-sustained. By way of review, in the learning objectives for section 1, we defined the 4 sides of the fire tetrahedron, which includes fuel, oxygen, heat, and the chemical chain reaction. We identified the 3 states of matter, which again is solids, liquids, and gases. We defined vaporization, which is the change of a state of matter from liquid to gas. We defined pyrolysis, which is a change in matter from a solid to a gas. And we defined a ventilation-limited fire, which is a fire that lacks oxygen and often occurs in today's residential and commercial fires. In section 2, the learning outcome was to explain the significance that the products of combustion have upon life safety. The objectives there included identifying the common products of combustion, which is smoke, heat, and flame. We identified the 2 most common toxic gases found in structure fires, which is carbon monoxide and hydrogen cyanide. And we identified the 5 characteristics of smoke, which is flow, volume, velocity, density, and color. We also explained the significance of each characteristic of smoke in assessing a structure fire, and you completed a associated activity. Now we're carrying on with section 3, and the learning outcome here is to explain the significance of heat released during combustion to life safety. The learning objectives are to define heat, to define heat release rate, to define heat flux, and to explain the impact of heat flux on civilians and firefighters during a fire. So in section 2 we discussed the general byproducts of fire, which includes heat, smoke, and light. In this section we'll focus on the heat produced by a compartment fire and its specific implications for life safety. Heat is a form of energy that is transferred between 2 objects or the regions of one object. Heat energy is critical to understanding fire dynamics. So there are 2 types of energy in general. There's potential energy and kinetic energy. Potential energy being stored energy, and kinetic energy is that possessed by a moving object. So it relates to fire. Think of it as if you're going to a campfire, potential energy is the piece of wood that's in your hand that you're about to put on the fire, and kinetic energy is the actual process of that fuel burning in the fire. So what do we call the measurement of heat? Most people would answer temperature. But temperature is in fact a measurement of kinetic energy, the measurement of how fast molecules or atoms are moving within an object. And this is measured in Celsius or Fahrenheit. Heat, however, is in fact measured in the metric system by the unit called joules. 1 joule equals the energy expanded by a force of 1 Newton acting over the distance of 1 meter. And 1 Newton equals a force that produces an acceleration of 1 meter per second on a 1 kilogram mass. In most fires, the amount of heat energy can be great, and is more realistically measured in kilojoules. So a kilojoule is equal to 1,000 joules, or stated another way, the joule to kilojoule ratio is 1,000 to 1. The transfer of heat energy. Heat is the amount of energy transferred from one object to another, or within an object, due to the difference in temperature. Heat is not transferred between 2 objects that are the same temperature. Transfer of heat energy can occur by 3 mechanisms. First, conduction. Second, convection. Third, radiation. We'll go over these 3 in more detail. Conduction is the transfer of heat within a body to another body by direct contact. The more tightly packed the molecules in a substance, the more readily it conducts heat. For example, glass or even wood are poor conductors of heat. Wood will burn, but it doesn't conduct heat well. But if you think about steel or copper, those types of metals, they conduct heat very well. Convection is a transfer of heat energy in a fluid, whether that be liquid or gas, to a solid surface. Combustion heats the air, making it buoyant, and thus that heat rises. This is the dominant form of heat transfer early in a fire's growth. And lastly, radiation. It's a transmission of energy as electromagnetic waves, such as light waves, without an intervening medium. Radiant heat travels in all directions. and radiant heat often becomes the dominant mode of heat transfer as a fire grows in an enclosure. This brings us to a very important concept when we think about the modern fire environment, and that's heat of combustion. Heat of combustion is the total amount of energy in kilojoules that is released when a specific amount of fuel is burned. Modern furnishings and contents that are plastic-based generally have more potential heat energy per kilogram in comparison to wood products. Closely related concept is heat release rate. This is the energy released per unit of time as a fuel burns. Two items may have the same heat of combustion. They may have the same number of joules that would be released when they burn. But if that item releases that energy twice as fast, it has twice the heat release rate. So you may have heard it said that today's structure fires burn hotter, again relating back to temperature. What in fact we see is that we have higher heat release rates. So it's not necessarily the temperature is higher than today's fires, but it's that we go to higher temperatures more quickly as a result of that higher heat release rate. So heat release rate is measured in watts or kilowatts. A watt is 1 joule per second, and 1,000 watts is equal to 1 kilowatt. So we have a chart here from NFPA 921, just shows us some of the peak heat release rates measured in kilowatts for different types of fires. For example, a small wastebasket fire would produce 4 to 18 kilowatts. A cotton mattress, 140 to 350 kilowatts. Again, cotton is a natural material. Small pool of gasoline, a hydrocarbon, is 400 kilowatts. Then we get into modern furnishings that we have in today's homes and businesses. Polyurethane mattress, as you can see, very high numbers there, 810 to 2,630 kilowatts. And a polyurethane sofa, which is 3,120 kilowatts. That's a very high heat release rate, and it accounts for why fires in today's homes and businesses is so dangerous. So this is a demonstration of heat release rate. So it's cotton versus a synthetic sofa that are lit at the same time. And we'll notice there the time frame, it's speed times 10, so this is not real time, it's been sped up. But we'll see the difference between the cotton sofa here on the left and the synthetic sofa on the right, which is a modern furnishing. So we have the ignition of the fires. We're going through that incipient phase. If this was this is in an open area, but if this was in an enclosure at this point, the room would be very much untenable. See, the most of the sofa has now been consumed. In fact, the entire sofa basically is consumed within 5 minutes. In the same time frame, the cotton-based sofa, which would have been found in your home 40, 50 years ago, and is still in the early growth phase. This video goes on for a few more minutes. Stop it here, but basically this fire on the left does not completely consume the sofa until the 30-minute mark. So we can see the difference, right, in the heat release rate. The heat release, or the heat of combustion, may be very similar between these two sofas, but the heat release rate in the synthetic material was drastically higher than the heat release rate in the natural fiber material. Next concept is heat flux. And heat flux is the transfer of heat energy per unit of area per unit of time. Heat flux is the heat rate per unit area, typically measured in watts per meter squared. So why is this important? Firefighter PPE, like everything else in the fire environment, is exposed to heat flux. Temperature is not necessarily our enemy, it's the heat flux that we encounter. Firefighter PPE is assigned a thermal protection performance rating. And all gear, no matter how well it's built, has its limits regarding how much heat flux it will tolerate. So the results of high heat release rate and high heat flux, it results in, for civilians, reduced escape times from occupancies. For firefighters, we have a small window of time to locate and extinguish a fire upon entry into a structure. Burn injuries and potential fatality is the ultimate outcome. Civilians are most likely at risk if they do not have the protective clothing and equipment that firefighters have. So in conclusion, joules is the unit of measurement of heat. This is not to be confused with temperature. Heat release rate is the energy released per unit of time as a given fuel burns. Heat flux is the transfer of heat energy per unit of area per unit of time. Heat flux accounts for burn injuries and potential fatality among civilians and firefighters during a fire. That concludes Section 3. We'll come back shortly for Section 4.